Okay, so let's get started again. So kind of in our structure of having a biomedical lecture first, which we had from Professor Patma, we'll follow up with a lecture that's really focused more on modeling and computation. And so we heard about the importance of scattering. Potentially, in some cases, it helps you. It gets you some forward propagating light scattered back and collected by your detector. But mostly scattering hurts us in that it distorts and attenuates our focal field. And so there are many approaches to try to understand this problem, and our hope is that as we understand this problem of how tissue microstructure can distort these focused beams, we can then use that knowledge to perhaps tackle this grand challenge that Professor Patma posed to us, which is to kind of mitigate the effects of scattering and improve the depth and resolution of images. So it's my pleasure to introduce Dr. Janaka Ranasinghe-Sagara. He's been a postdoc here at the Laser Institute since 2010. Prior to that, he was at the University of Edmonton in Alberta, Canada, working on optoacoustic imaging. And he received his doctorate at the University of Missouri, where he developed electromagnetic wave propagation models to look at structurally anisotropic tissues. And so I'll give it to Janaka to give a complimentary lecture.
I'm going to talk about modeling focus beam propagation in scattering medium. In this lecture, I'm going to do a short introduction. After that, we will look at some basic things, Maxwell's equation and then wave equation. After that, how plane wave and focus beam propagation in a free space. Then we go to the scattering medium and look at how plane wave propagate in a scattering medium. Then how focus beam propagate in a scattering medium using two different techniques. One is FDTD solution to Maxwell's equation. Other one is developed by our group, that's a Huygens-Fresnel wavelet method. So we'll look at that one too. Oh, it's upside down. So it's supposed to go in the other way. So this is supposed to be here. Anyway, so the focus beam, when we have plane wave, it goes through the lens and then refracted into focal spot. When we have a scattering medium, this focal spot is getting blurred. So Eric talked about those things in detail, so I'm not going into detail. What happened is, when this wavefront, this focus wavefront is propagating, there's a scatter in the medium, and this scatter propagate a scattered field. The incident focus beam is propagating upward. After that, this scattered field and the incident field combine together and provide a distorted field, and it propagates further. So it is hard to imagine, because when you see incident field, there's an object, we see a shadow, but in microscopy, this incident field is propagating. So when we want to get the distorted field, we get the incident field and then add the scattered field. So that summation, the superposition of a scattered field and the incident field provide the distorted field in microscopy. So what we are going to do is understand this distorted field. So we have to start with the fundamentals. We are going to go with Maxwell's equation. Yesterday, Vasan talked about Maxwell's equation in detail. I'm going to go and look at these equations, and then we are going to look at wave equation and plane wave from plane wave solution and focus beam solution from Maxwell's equation point of view. Maxwell's equation provide exact model for electromagnetic wave propagation. So in microscopy, we are in that corner that Jerry showed you yesterday's lecture. in that region, we have Maxwell's equation provide the exact light propagation. It is, but when we go to the larger spatial scale, this Maxwell equation is averaged out, and those features are washed out. So, because, okay, let's get into the Maxwell's equation. First one is Faraday's law. Okay, this one, when there's a change in magnetic field, it produces an electric field. The second one, when there's a change in electric field, it produces a magnetic field. And also, if there's a current, that also produces a magnetic field. The third one, when there are free charges, that create an electric field. The fourth one, in a magnetic field, when you enclose that magnetic field, there are no net flux going out from that enclosed surface, because whatever the magnetic lines coming in are going out, they are never ending. So these are the four Maxwell's equations. When we consider no flow of current and no free charges, we can get this equation, because when there's no flow of current, this J becomes 0, then we can write that equation like this. When there are no free charges, then this dot product becomes 0. We can use those equations and apply, substitute this H by the second equation and get this kind of a relationship. And in this relationship, this 1 over square root of mu naught epsilon naught is equal to the speed of light in the vacuum. So you can finally get an equation in this form that is known as wave equation in free space. So let's look at what are the solutions for this wave equation. In general form, if any function which is r minus ct, r is the space variable, minus ct is a solution to this wave equation. This is the plane wave solution. We can write plane wave solution like e naught exponential ik times z minus ct. This k is the wave number, it is a vector, k is a vector propagating along the propagation direction, and its value is given by 2 pi by lambda. So we are going to use this wave, plane wave, in the propagation. If you look at the plane wave, this electric field is oscillate like that in a xz plane. And then the magnetic field oscillate in a perpendicular direction, this YZ plane. When t equals to 0, any given time, this electric field is propagating. For example, if electric field is propagating from here to that end, this first row gets 0, the second row may get the peak, and the third row gets 0, like that. It is propagating, and in a given location, this first, let's say, take this first row, at given location, it gets 0 peak and 0 peak, like negative peak, like that. So that's how this plane wave is propagating. And at given time, we can simplify this equation to E naught exponential I times k, and given location, we can write the equation like that. This kc is omega, which is angular frequency. let's look at other properties of this plane wave equation. We can get the amplitude, E naught, this is the magnitude of E naught exponential ik times z minus ct. This exponential I times this part, this is, we can say that one as angle theta. Magnitude of that value is always 1, because exponential I theta is cos theta plus I sin theta. Magnitude of that value is always equals to 1. So the amplitude becomes E naught. And then when we want to calculate phase, it gives the ratio between imaginary value and real value, and get the arctangent of that angle. That gives a phase. That's why we use this I theta form. So anytime we want to calculate the phase, we can use this equation and calculate the phase. Then energy of this plane wave is given by half times real component of E cross product of H, and it is equals to half times epsilon naught C E naught squared. You can see that square, it's cross. So that means the energy, or the energy propagating towards and hit on something, if we have a detector, then we can measure the energy. That is proportional to E naught square. That means it is proportional to the electric field. So by working on electric field, we can we can either work on electric field or magnetic field, because energy can be, say, in magnetic field. So we can use either magnetic or electric field and work from there. In our case, we selected electric field, and we are looking at how electric field propagate in a free space and in a medium. Polarization. Polarization is described by specifying orientation of the electric field. Yesterday we learned that we can have linear polarized light. It can be X polarized or Y polarized due to based on the reference, we can say it is parallel or perpendicular polarized light. In this case, it is X polarized light. It is parallel to X axis. So the Ex component is given by E naught exponential IKZ, and the perpendicular component is equal to 0, Ey equal to 0. When this polarized light go and hit on a scatter, we can the scattering field goes in every direction. Scattering field scattered into every direction. We can consider one scattered direction, this W direction, and we can draw this plane that is the scattering plane. Then the incident on this scattered plane is U and V. Those are the two polarization component incident on this scattered plane. We need to calculate U and V. To calculate that one, if we have X polarized light, we do the vector decomposition. So the EU is E naught times cos phi, and EV is minus E naught times sin phi. So those are the two components act on this scattered field. We will come across these things in the later part of this lecture.
Shanika, can you just tell us what the relationship between UV and W are? How do you draw U and V based on W?
Okay. So the W is the intercept direction, that is the scattered field going on. So and this W is phi. X and W has an angle, that one is phi, and then we get the plane that goes lies between W and Z. So that is the scattered plane, and then the plane U is the polarization vector parallel to that plane, and then V is the polarization vector perpendicular to this scattering plane. Okay, now we come to focus beam propagation in free space. This is our incident light. It is X-polarized light. It is in a medium of N1, and then hit the objective lens and propagate toward the focus. This is in free space. Here, the wave vector k is along the propagation direction, and these are the polarized component. Here, n theta is going out of the cone. So this one is like a cone, and n theta is going out of the cone, and phi is the like the tangent in the cone. This n phi. So and it goes toward this way. Theta max is the maximum angle, and this length is equals to the focal length. And these red dots are a convergent spherical wave propagating toward the focus. Now this dotted surface at the lens is not just a xy plane 2D spherical curve section, but it is a spherical cap. So you can consider like a sphere, and then cut horizontally we get a cap. So that kind of a cap we have right here. So the length of from here to there, that length is given by the diameter of the lens. And, when this electric energy hit on this lens, it is refracted. So there's a relationship between the energy enter in and going out. We can but energy is conserved, so we can apply this that relationship, and we can get this equation. So these are this is the refractive index in the medium, N1 is the refractive index in incident side. Normally it is equals to 1, and EI is the incident electric field. So we can calculate this is the amplitude of the electric field at this spherical cap. And then we have to consider the polarization component. This is X-polarized light. When it comes to here, the phi start from x-axis and goes along this circle. So this cos phi and theta is the X-polarized component at this location when you consider that location, and n phi gives the y component. But after 90 degrees, this n theta is going inside the screen, and n phi is coming this way. So these angles are changing. Then phi becomes 90 degrees. This cos 90 becomes 0. So there's no theta component along this direction. Only of n phi component. This n phi is going to be 1. So n phi is going out at 90 degrees. So this is how the polarization component work in focus beam. And this electric field is propagating toward the focus, and electric field at any location in this area is given by this equation. This is in cylindrical coordinates. Let's look at this equation in detail. So if you look at this section, this one has amplitude, exponential part, I times some kind of complex thing. Let's say this one has theta. So it is similar to a plane wave. This one has the same form of plane wave. And then we integrate from 0 to theta max and 0 to pi sine theta d phi d theta. That means we consider plane waves emitting from this surface, and then we integrate all plane waves, and at any location the summation of these plane waves gives the electric field. So that's how we can see this equation. And then let's look at this part. Okay, this is the electric field at the lens surface. We calculated that part. And this exponential part, it has I theta value. This is the k vector, which is going along that direction. Normally we use kz, but in this case, k is going along different direction. If it is starting from here, it is going in that direction. If it is center, then it is going along z direction. So we have to decompose this k vector along z direction and then rho direction, because we are using cylindrical coordinates. So we can use x and y and define a rho, and so this is a k vector along rho direction. So this part is the phase with respect to origin. Let's set this z equal to 0 and rho equal to 0. So then this part becomes 0. That means the phase at this location is 0. Then at any location, any other location, then there will be a value for z and rho. You get the phase at that location. So that's why you can call this is phase at any given phase at rho, phi and z with respect to origin. So this part is exponential ikf. F is this distance. So we set the phase at 0 at this plane, this actually spherical cap, and then the phase is propagating and goes to the focus. So this gives that phase. So this part is given the phase at the origin with respect to the lens. And we multiply by f. For that one, let's imagine we have a spherical wave emitting from this point. So spherical wave is going out from that point. That means there's an energy at the center, and when you calculate the energy at a sphere distance r from that spherical source, that energy is going to be the same energy as the emitting energy. So we need to take that total energy and divide by 4 pi r squared to get the energy. So that means we need to divide by r squared to get the intensity. When you talk about intensity, for amplitude we need to divide by r, the square root of that area. So when we have a spherical wave, the energy is decreasing along the distance, but in this case we have a converging spherical wave which is going toward the focus, so we need to multiply by this distance. This is our r, in this case this is f, so we need to multiply by f. So that's what, so that is the relationship given in this equation. So this is the focus beam propagation in free space. This is the analytical equation, so we can simulate that one and get the focus beam propagation. So now I said this spherical cap produce plane waves. So from this point we have plane wave and another plane wave starting from the middle goes to the focus. What happens is all these plane waves travel same distance. So at this focus they constructively interfere and produce a high intensity spot. That gives the highest intensity at the center. And when we go out from the center, at this location, this one travels further, this one travels longer, and the center one travels shorter, so there will be destructive interference, and that gives a smaller intensity. This gives the Airy disk pattern at the focal plane. How do I follow? Okay. So this is the radius of Airy disk. R equals to 0.61 lambda by numerical aperture in microscopy. In a confocal microscopy, these are the values. Then the next one is numerical aperture. Numerical aperture gives the angular extent of the lens. It is given by n sine theta max. Let me go to this video. So in this one, we will have a small numerical aperture lens. N is given by n sine theta. In this case, numerical aperture equals to 0.25. And when we increase that one into 0.85, you can see this beam is this angle is become larger, and the beam is tightly focused. So the numerical aperture, when you increase the numerical aperture, that increases the resolution. However, it decreases the probing depth. You can see in this one has a larger probing depth, and this one has a shorter probing depth. And here we use numerical aperture for the Airy disk radius calculation. So when we have a larger numerical aperture, we have a smaller Airy disk radius. That's why we get a higher resolution. Okay, now in this section I'm going to concentrate on a medium containing the light propagation in a medium containing scatterers. So here we consider a linearly polarized electromagnetic wave with a unit amplitude propagate along z-axis impinging on a scatterer. This scatterer is not a spherical scatterer, it can be any shape. So this plane wave comes in and hit on this scatterer. Then we can place a detector here. This detector can capture parallelly polarized light and perpendicular polarized light. So if we have only parallel polarized light, and then we can set this one to measure parallel polarized light, this S2 gives the relationship between incident parallel polarized light and detected scattered parallel polarized light. S3 gives the relationship between perpendicular incident parallel polarized light and perpendicular polarized light and scattered parallel polarized light. So this is the relationship given for non-spherical scatterer, and we can write the same thing for perpendicular scattered field. We have S1 and S4. The incident component is decomposed into this cos phi and minus sin phi component, similar to what I showed in earlier slides. You can put it into a matrix. If you see any scattering book, you will see this formula. This is the relationship between incident polarized light and scattered polarized light. Now we replace that scatter with the spherical scatterer. Then the scattered field is given by this kind of relationship. Here we don't have two components, we don't have perpendicular component because of this spherical nature. Only parallel incident light provides parallel scattered field, and perpendicular incident light provides perpendicular scattered field. So we can put this equation into matrix. So you can see this is the relationship we get. So we have S1 and S2. This one is called amplitude scattering matrix, and if we know S1 and S2, we can calculate this scattering field, whole scattering field for any given theta and phi. The question is how to calculate this S1 theta and S2 theta. For spherical case, we have a Maxwell's Mie solution to Maxwell's equation. We can use Mie solution to calculate that S1 and S2. Mie solution is analytic solution to Maxwell equation in spherical geometry for a plane waves incident. So that is important. This one is not defined for a focus beam. This is defined for a plane wave. And it describes the scattering of electromagnetic radiation by a sphere. And it gives a solution that is an infinite series. However, it converges, so we can use that one. And this Mie solution provides both internal field and external field at any given location. So if our scatterers are spherical, then we can use this Mie theory to calculate the scattering field. Okay, I'm not going to explain this equation, but to show how complex these Mie equations are, just put these equations down. This is the S1 theta, so we need to calculate S1 theta and S2 theta. These equations show the relationship between a scattering angle and other component. Here the Pn cos theta is first derivative of Legendre polynomials, and these are the coefficients we calculate for the infinite series An and Bn. An and Bn are related to Bessel functions, actually Riccati Bessel functions. So we can calculate this An and Bn and substitute those values here and calculate S1 and S2. So we use this. We used that program yesterday when we calculate the scattering particle intensity, amplitude, and the scattering cross section. What that program did was calculate S1 and S2, and then out of that we calculate that profile. So the S1 is the parallel component, S2 is the perpendicular component in the far field. So this is in the far field. That is very important because we will get a different equation in near field. Okay, so let's talk about a little bit about yesterday exercise. So in that one, we have parallel polarized light, and then it is coming in this direction. This red one is the detection field, and then we saw two lobes for the perpendicular polarized light, and we saw a circle for parallel polarized. Two lobes of parallel polarized light and a circle for perpendicular polarized light. So this is what happening parallel polarized light comes and hit on a smaller scatter, it provides dipoles, and dipoles are shaking in this direction, along x direction, and it produces a scattering field like that, and we get the our detector is in this plane, xz plane, and we get that results. That one shows two lobes, and in this case, the perpendicular polarized light comes oscillates along y direction, comes in, and then dipoles are oscillating in y direction, and it produces this kind of a donut, and we get the cross section along this plane, and that gives a circular shape. That's why we get two different shapes for parallel and polarized light in yesterday's exercise. And another thing is input for far field solution. These are the three parameters we input for far field solution. One is size parameter. It is 2 pi times n in the medium, in the radius of the particle divided by lambda. So if we keep this ratio constant, we will, and then for specific relative refractive index ratio, we get the same curve. Here I keep this ratio equals to 1, and then we get the same curve. So when you double the radius, you can double the lambda, and plot that one, you get the same curve over and over. So this is the relationship between particle radius and lambda. That is in far field solution. Now, when we come to near field, in microscopy, the particles are close to each other, so we need to consider a near field solution. We have an extra component that is given by this distance parameter, 2 pi n times r divided by lambda. R is the distance from the center of the particle to the distance we are interested in.
Jonathan, with that distance parameter, can you give us some insight as to at what value of the distance parameter you transition from the near field to the far field solution?
Normally, it is 2 to 3 times lambda. Within 2 to 3 times lambda, we have a near field. We have a intermediate field effect. But beyond that, after 20 times of the radius, beyond 20 times of the radius, then it becomes a far field.
20 times of the radius or 20 times the lambda?
20 times of the radius, actually, because when radius is getting bigger, you have that intermediate effect in between.
And that's independent on the size of the particle relative to the wavelength?
That is hard to say. I haven't tested that one, but I have seen that when I increase the size of the particle beyond 20 times, we can see it is converging into the far field solution. Because when we take the far field solution, we get the Hankel function and then use asymptote and get asymptotic solution for the Hankel function. So it's hard to say that it varies with the size of the particle and lambda. So now we have some basic components. We know plane wave solution and how focus beam propagate in a free space, and what happened when plane wave hit on a spherical particle, how we get those S1 and S2 from this Mie theory, and we are going to look at another approach. This is FDTD solution to model light propagation. So one way is using plane wave analytical equation, solving different do the solution and get equation that is Mie solution. And this is another way of doing that. This is FDTD solution to model light propagation. FDTD means finite difference time domain solution. In FDTD, Maxwell equations are implemented in Cartesian space grid, and we use time-stepping leapfrog approach. So we define the solution in a Cartesian space, and then we do time-stepping propagation, and it simulates continuous electromagnetic wave. So we start from initial condition and propagate towards the region, and this one is very good for modeling small volumes because the computational cost is so high. If you consider a big volume, it will take long time to do the simulation. So it is very good for small volumes with inhomogeneous tissue structures. And there's no linear algebra is involved, so there's no matrix inversion and those kind of things. And the way the FDTD is doing a simulation, we can do we can parallelize those equations and increase the speed. Earlier we saw the wave equation in free space. Now we are going to do simulation in a medium, in a scattering medium or any other medium. So now if it is non-magnetic, this mu node is not going to change, and the epsilon node is going to change. The new epsilon is given by epsilon r times epsilon node. The epsilon r is the relative permittivity. So now our medium is going to change. The dielectric is going we are going to go in a different medium. So we have a different epsilon node. We can substitute that value in this equation and get a different relationship for wave equation. Here we use v, that v is speed of light in that medium, and it is equals to 1 by square root of mu naught epsilon r epsilon node, and 1 over square root of mu naught epsilon node is c, and it is c divided by square root of epsilon r. Epsilon r is, square root of epsilon r is equals to the refractive index of the medium. This is how we get the relationship between optical properties and the dielectric constant. We are going to do 1D FDTD solutions for Maxwell equation. These are the two equations we derive, and then we consider 1D model. In a 1D model, d by dy equals to 0, d by dz equals to 0. So these two become 0. So left hand side is given by this section, this part, and the right hand side is given by this part. So we can do this equation and get these kind of relationships. So this is for the other equation, for magnetic equation. We can do that one, and we can get these four relationships, and we can pair them. These two gives the relationship between EY and HZ. On the right hand side, you get the relationship between EZ and HY. So we take one pair of equations and do the simulation. So we have initial conditions. We know initial EY and HZ. Let's start from here. So this is the spatial derivative of HZ. That is the spatial. Let me describe the axis first. This horizontal axis is x-axis. This vertical axis is time axis. So this when you get the derivative of these two, that gives this section, and this part is given by the derivative along the time axis. This one. So we know this initial condition. We want to calculate the next one. So we have these two values and the initial EY, and apply that one to calculate the next EY value. Then we know that value, same way we can calculate the next value. We apply the next equation and calculate the next HZ value. This is the time stepping leapfrog method. This is how we do simulation in FDTD in one dimension. In 3D solution, we define this volume as a voxelized grid. And in this voxelized grid, we put a perfectly matched layer absorbing boundary condition. We do that one because when this electromagnetic wave propagate and come to the boundary, they bounce back. So when we have absorbing layer, this we can match that one, and so there's no effect on the return electric field or magnetic field. So I show that one in color. And then we assign a dielectric constant at different locations. So here, when we have different particle in this volume, we can assign dielectric constant for that different regions. And if we take one voxel, it's going to look like this. All the edges are represented by electric field, and the surface are represented by magnetic field, and they are propagating in these directions and at each time step. One way to calculate, this is one method, one way to calculate the scattered field is you get this Maxwell's relationship, and then you inject the incident field like that. So this is the current. In this one, if the relative dielectric constant is larger than 1, you have an incident electric field, and you at only that location you inject that electric field. So you use this technique in the simulation and get the electric field. To do the electric field simulation, you have to start from one end and go all the way up. So after that, you can look at electric field at any given plane, either this way or that way, either X, Y, or YZ planes. This is how we do electric field FDTD simulations to calculate electric field or magnetic field. Let's look at the results of FDTD solution and Mie solution. In this simple case, when there's a spherical scatterer, we have a plane wave incident, and we get the perpendicular and parallel component. And in this case, we can change the grid spacing. In first image, grid spacing is lambda by 10, the second one is lambda by 20, third one is lambda by 30. As we decrease the grid spacing, that means the spacing, when we decrease the grid spacing, this FDTD solution merge with the Mie solution. So this is an important concept. So we cannot have bigger grid spacing in FDTD. We need to have a smaller grid spacing to get accurate result. And also the grid spacing also apply for the stability of the propagation. So if you don't use proper grid spacing, you don't get stable results. In this case, a plane wave propagation in a scattered medium. This is the incident wave, and this is nucleus and cytoplasm, and these are organelles. You can do FDTD simulation and get this kind of results. And this was done by Andy Dunn's group. And you can see the amplitude change in far field for cells with organelles and cells without organelles, how they are different in two different cases. And in this case, they have 3 different nucleus and organelles, and they did simulation. Here is a non-scattered medium, so focus beam is propagating in this direction. You can see it gives that nice little focal volume, but when there are scatterers, this medium is distorted. For this simulation, the simulation time of this simulation is 500 process hours. So that is one major disadvantage of FDTD simulation: long processing time. This is another case. This one has 7 nucleus and organelles. And in this case, this is what happened to the focal volume. It is distorted in this case. Simulation time is 5,300 process hours. It does not take that much because they use parallel processing and reduce the time. So in this case, they use 128 processors. So the time is reduced by, when you divide this number by 128, that's the number that's number of hours they use to do the simulation. So the problem with this FDTD approach is you need enormous computational resources, not only process hours, large memory, and you need to have a small time step and small spatial steps, that means voxel size, to satisfy this leapfrog integration. And other thing is you need to assign the dielectric constant at each voxel. In certain cases, this dielectric constant does not fully cover the voxel, but you need to decide whether you put the whole voxel or not. It's going to be either whole voxel or not. So we will have this kind of a digitization errors when you have that problem, like this kind of a non-smooth profile for non-rectangular materials. To overcome those problems, we decide to use another approach. This is based on Huygens-Fresnel's principle. In Huygens-Fresnel principle, each point of advancing wavefront front is a wave with the same phase. So when we advance that one, at any given location, we can any given location in that wavefront, we can assign a source, hemispherical point source. So here we assign a hemispherical point source, and here we assign a hemispherical point source. So we can assign large number of infinite number of hemispherical point source along that wavefront. So those hemispherical point sources are propagating, and they provide a plane at different locations. In all other locations, they are destructively interference and negate the effect. So this is for the plane wave. This one is for the focus beam. So this is not just XY plane thing. It is a 3-dimensional thing. So this wave is a hemispherical. So it is going out like that. So we try to use Huygens-Fresnel ray representation. So we define a ray, and so at each point source we define infinite number of rays emitting from that center. So we use that definition, we define in that way, so we can work with rays instead of complete wave. So now instead of using instead of decomposing wave, now we have we have a combination of rays. We can use that one for our simulation. This is how we implemented that one in non-scattering medium. So this is a spherical cap I mentioned earlier. So all the waves are emitting from that spherical cap, surface of the spherical cap. Now we can take one location and generate infinite number of rays, but to improve the efficiency, we get one ray that go and hit a detector. So we place a detector wherever we need. We can put in the focal plane or any other plane, and then we get one location of the detector and take the ray that hitting on that location. So a ray from this point hit on that location, and then a ray from that point goes and hit the same location like that. So we do these things for the whole area of the detector. And then as this ray propagate, we advance the phase, because in plane wave propagation, we learned that it is E naught times exponential ikz. So as this ray travels that distance, the phase advances, we calculate the phase at this location. So at this point, the different these rays travel different distances and provide constructive and destructive interference, and provide the final amplitude at that given point in this detector. So we verify our results with the analytical solution. This is the analytical solution results. We have three components: Ex, Ey, Ez, and these three are amplitude. This is phase. The first row is analytical solution results. The second row is our technique. We call our method as Huygens-Fresnel ray-based electric field superposition. You can see there's a very good match with these two, this new method. So that gives us to use this method for scattering medium. As I mentioned before, the focus beam is a combination of plane waves. So when you put a scattering particle at this any given location, we can consider these rays as a parallel wave, so plane wave. So this plane, we already know the solution for plane wave impinging on a spherical particle, that is the Mie solution. So we can apply Mie solution to get the results. So this, we know the Mie solution, so we can apply Mie solution and get this kind of a function. So we can place a detector right here and capture the results. So this is the way we do the implementation for a medium with spherical scatterers. So we generate points in this spherical cap, and then project rays from each radiating source to scatterer. So we project this one at each scatterer, and it creates a scattering field. Then we get the interested location in this detector and calculate what scattering angle this ray is going into, and then use Mie solution to calculate S1 and not S1 and S2. This is a near field. We calculate parallel and perpendicular electric field and store that one, and do the same thing for next ray for this scatterer. Then we add everything together and get the electric field at a given location. We apply our technique for 4 cases. In first case, we place a particle on the optical axis. The second one, it was shifted by certain distance. And the third one, we place the particle further away from the detection plane. And the fourth one, we put 2 particles. And okay, in this one there's no XY detection plane. The detection plane is like that, right here in XY plane. We compare these results with FDTD solution. This is for case A for 2.5 micron particle. This one is for 5 micron particle, case A, case B, case C, case D. You can see the similarities between 2 methods. The important thing is to calculate, to get this result, we need to spend 2000 processor minutes. That's about 330 hours, processor hours. But we can get this result in a minute with this resolution. But we can, if we reduce the resolution, we can get those results less than a minute. So in these results, we want to compare one by one and to get the error value. So this one takes 1 minute, but we can always get a quick snapshot of the results by reducing the resolution. Okay. Here we show that we can get different slices. We don't need to do the whole simulation to get these results. We can put different detectors. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 detectors. And then those are XY plane detectors. Then we have 2 more detectors in XZ plane and YZ plane, this side ones. And we can do this simulation and get these cross sections. We can see how this focal plane, focus beam is propagating at different levels. Z equals to 0 is at the focus. This is the focal volume. And when you put a particle, you can see how this focal volume is distorted, and at each plane this electric field is distorted. You can get all those information using this new method. Pros, this method is 2 to 4 orders of magnitude faster than FDTD solution, and we don't need high performance computer system to do simulations. You can run this one in your laptops, and you will do your labs in desktop this afternoon using this tool. This is one variation of that tool, and it does not require to simulate complete volume, so you can put different detectors at different locations and get the results. So if you reduce the resolution, you can get a quick snapshot of this electric field distortion. But the problem is you need to know the complete amplitude scattering matrix to do this simulation. In FDTD, you don't need to do that, because as you propagate, you take care of dielectric variation and you do the simulation. But in this case, you need to know this information to do the simulation. So in a summary, we discuss Maxwell's equations and solutions to Maxwell's equation, wave solution, and then Mie solution and FDTD solution. And we discuss what is the plane wave and how it propagates, and then focus beam propagation in free space. Then we discuss FDTD solution to model focus beam propagation, starting from 1D model, then go to 3D case, and the basic equation they use for focus beam propagation. And then we discussed the Huygens-Fresnel wavelet to model focus beam propagation.